We will continue with our second lecture on model predictive control. In the last lecture, I introduced the basic idea of model predictive control, contrasted that with the PID control idea that we have been teaching in this course. I made three important points about model predictive control. Number one, a model predictive control uses an explicit model. Number two, there is this notion of horizon which is introduced in model predictive control, which is usually not seen in PID control. And number three, while in PID control, the control law, it is an analytical equation. In model predictive control, the control law itself is a solution to an optimization problem. So, these are the three major differences between a standard PID control and model predictive control. As I said before, model predictive control can be derived for single input single output systems, and model predictive control can also be derived for multiple input multiple output systems. In fact, one of the advantages of model predictive control is the formulation is pretty much the same, nothing changes much when you go from CISO formulations to MIMO formulations. That is a big advantage. The other advantage, which we will not see as much in this course, but which is of real relevance, is that when we go from linear systems to nonlinear systems, the theory that underlies control pretty much remains the same. In fact, the formulation is absolutely the same. In one case, you will be solving optimization problems with linear models. In the other case, you will be solving optimization problems with nonlinear models. So, in that sense, once you understand optimization theory quite well, whether you are designing a controller for a linear system or a nonlinear system really does not make that much of a difference when it comes to model predictive control. Contrast that with traditional control approaches. For nonlinear control itself, there are so many different techniques that you can think about, each of which comes its own theory. So, if you take the other approaches, you have to kind of keep learning different ideas for each type of formulation. Here, however, an optimization formulation directly gives you a solution to this problem, and once you understand how to solve optimization problems well, then whether you are doing control for linear or nonlinear systems does not matter quite a bit. Okay, so with that, what I am going to do is we are going to go and then look at a picture which is very important. This is a picture that is useful for understanding MPC quite well, and I will explain the idea of MPC using that picture, and then we will talk about how to actually formulate each one of the ideas that is there that we learn from this picture. So, the idea of MPC is the following. In this picture, I am going to kind of explain each one of this. So, first let us look at CISO system, right. So, we will look at CISO systems, and you will see how easily we can extend this idea to MIMO systems and so on. So, in this picture, if you break it into two halves, the first or the top half is plotting the control output y, and the bottom half is plotting the manipulated input u. So, that is the first thing to notice. In the x axis, you have time steps. Okay. So, I am going to introduce this notion. This is slightly different from the continuous time formulation that we have been seeing till now, and I will explain what this means. First, I will explain all of this conceptually, and then we will talk about how you build a model for this and all that later. Okay. So, x axis represents the different time steps. The first half of the y axis y is plotted. The second half or the bottom half of the y axis I am plotting u, and then we have to denote what current time that we are at. So, t equal to k is the current time step that we are at. So, anything in this direction is the past, things that have happened, and anything in this direction is the future, things that are waiting to happen or will happen. Okay. Now, when we remember when we did all of these plots for u and y, I have shown you many such plots. So, I have said y goes like this, maybe u goes like this, and so on. So, when we do this, when we talk about continuous time formulation, at every time there is an input and there is a corresponding output. So, that is how we think about this continuous time formulation. However, if you think about controllers that are operational now, and in fact controllers where computers do the computation for moving the actuator, the control moves are not realized at all times like this instantaneously changing. What happens is we make these control moves at pre-decided times. That is how most of the current controllers are implemented. So, this is a difference from what we have been seeing till now. So, till now we have been looking at u being a continuous variable with respect to time, that is continuously changing with time, and correspondingly y also continuously changes with time. Now, u is in our control, right, we are making changes. So, basically what happens in systems nowadays is that let us say this is time t equal to 0, you can arbitrarily choose any time where this controller starts to work or it starts operating. Now, what we do is we basically figure out what is the control move that I need to make at time t equal to 0. So, I make that move, and then basically in most systems what I do is I hold this to this value. So, see the difference between the PID kind of pictures that we have been seeing and discrete nature of the control move that I am talking about for the first time, right. So, physically what you are going to say is if there is a tap that you are opening as a control valve. So, what you do is at time t equal to 0 you open it little bit and then hold on to it, and then what you do is you decide the next sampling time. Okay. So, this is called Ts, next sampling time at which you are going to think about making the next control move. So, you could make the control move up or down. Let us say you make a control move up, then what you do is you hold this till the 2 Ts, the second instance of the sampling time, and then maybe you make a decision and then you hold like this and then you make another change at 3 Ts and so on. So, the changes that you make are at discrete intervals. This is something that is different from what we have been seeing till now, because what we have been seeing till now is looking at this as continuous functions of time, but for the first time we are saying that these are changes that are made at continuous discrete intervals of time. Now, in reality whenever you do computer control, digital control nowadays, you basically make these discrete control moves. So, from a picture of u versus t viewpoint, there is nothing that changes. If you have continuous control, you keep changing u at all times with respect to time. In discrete, you have to choose this sampling time and then you keep making these changes at these sampling times. Now, you will notice obviously if I make this sampling time smaller and smaller, you will make the system more and more continuous, right. So, if Ts is 1 second, then you are basically making a control change every 1 second, but if the Ts is 1 millisecond for example, then it will look lot more continuous when you plot this in this scale. Nonetheless, there is absolutely no difference. Basically, you might want to think of as this time profile for u has now these discrete steps, and the time at which you make these discrete steps t, we call this as k Ts. So, k equal to 0, t equal to 0. So, that is the first time we make the first move, then k equal to 1, t equal to Ts. So, the second time we make a move, k equal to 2, t equal to 2 Ts and so on. The third time we make a control move. So, if you ask what will happen to the u between 0 and Ts. So, between 0 and Ts, whatever is a move I made at time t equal to 0, u 0 will be the value of u in this interval, and after Ts u will be u the move I make at 1, and after this it will be u move I make at 2 till 3 Ts and so on. So, this is how you can actually get a value for u at any time. It need not be only at the sampling time, you can get a value at any time. However, the changes are made only at those sampling instances, right. So, that is the key idea when you go from continuous to discrete. Now, let us look at what will happen to this picture y. Y will react to this, but y is a physical variable. So, y will keep changing based on these control moves you make. So, if you are looking at the height of the tank, so height of the liquid in the tank, you will notice that whenever you open close the tap, the height will start changing, going up and down. But we know for each of these changes the behavior is going to be kind of, let us say if it is a first order behavior, you know if it is a step, the first order behavior will go something like this, and then for a while it is going to stay, and then once I make the next change, the thing is going to change like this, and maybe it will change like this and so on. So, y will keep changing like this based on the changes that are made in u, and while y keeps changing in an MPC framework, what we assume is also that we take a measurement for y not continuously, but at the same time instance that I do my control move. So, the measurements also are available at only those times. However, between these times the measurement the actual physical variable will be having certain dynamics based on the standard. Whenever you change a u step, what will happen to y, that will keep happening, but you are only measuring at times Ts, 2 Ts, 3 Ts and so on. So, this is how you move from a continuous framework to a discrete framework, where everything is happening at all times. Okay. So, that is not changing, but the control moves are made only at discrete time intervals Ts, 2 Ts, 3 Ts and so on, and the measurements are also made at only Ts, 2 Ts, 3 Ts and so on. So, basically what this means is that when you compute an error between y and y set point, since you are not measuring throughout the interval, you have errors that you can compute at E of Ts is a time at which you can compute an error, which will be the measurement at y of Ts minus y set point minus measurement at y of Ts. Similarly, you can compute an error at 2 Ts, error at 3 Ts and so on. So, again see the difference in the previous PID case, we said we will keep computing the error at all times, that is how we got the integral and differential and so on. Here the errors are also computed at discrete time intervals, because the measurements are made at discrete time intervals and you are comparing these measurements with the set points at discrete time intervals. Okay. So, this part is a very important first step in understanding MPC, and this is another difference between PID and MPC. However, you can actually implement PID in a discrete form also, and you will see that in your lab work that goes with this course. MPC is mostly talked about only in the discrete framework. So, to summarize, discrete framework does not change anything physically in the sense that u and y are continuously changing, but you make these changes in u which is in your control only at discrete intervals. So, basically this will be the u profile, time profile. In response to that, y will be doing its own dynamical thing, you only measure the y at Ts, 2 Ts, 3 Ts and so on. Okay. So, now we have understood this, let us come back to this picture and explain what this picture means. So, what this picture says is I am at a current time t equal to k. So, we now write time as 0, 1, 2, 3, 4, k, k plus 1, k plus 2, k plus 3, k plus m minus 1, k plus p and so on. So, what basically this means is that when I write time t equal to k, it is actually k Ts, where Ts is the sampling time that we talked about. Okay. When I say t equal to k plus 1, that is k plus 1 Ts, when I say t equal to k plus 2, that is k plus 2 Ts and so on. Okay. So, since we do not want to keep repeating this Ts everywhere, we have simplified this and then said time equal to k Ts. Now, the MPC idea is the following: at time t equal to k, I have already got, let us say, a measurement value here, okay, and I am planning to make a control move, and I am planning to make a control move at time t equal to k. So, this is a control move that I am deciding what I should make. So, I want to decide this control move in such a way that when I get measurements at k plus 1, k plus 2, k plus 3 and so on up to a certain horizon, which is what we talk about. This is into the future, and I have a horizon, and what I want to do is I want to make a control move in such a way that when I get these measurements in future at time k plus 1, k plus 2, k plus 3 and so on, I want the error between these measurements and the set point to be as small as possible. Okay. So, that is the basic idea. So, the key difference between PID and MPC is that in PID basically we might be interested in this error. Now that this measurement is already there, I cannot do anything about this. We might say this error between y measurement at this point and y set point, we want that to be a small value, is something a PID controller might want. However, in MPC what we are saying is we are not only looking at what measurement I will get one time step ahead, I am going to be looking at measurements that I will get p time steps ahead. Okay. So, if I start from t equal to k, the first measurement I will get one time step ahead is k plus 1. Okay. This given k basically means I am sitting at k in very simple terms, right. So, all the computations are being done when the time is t equal to k Ts. Okay. Now, instead of just saying I want y of k plus 1 given k to be close to set point, what I am saying here is I want y of k plus 2 given k meaning I am at time k also to be close to set point all the way up to y of k plus p. So, k predictions into the future, I want the errors between those predicted measurement values and the set point to be as small as possible. So, if that is as small as possible, then the actual measurement will be close to set point. Okay. So, this is the prediction horizon. So, we will keep coming back to this, you will understand this better once we do the formulation, but this picture is very critical to understand. So, if you understand this picture then it becomes easy as we describe the other things. Okay. So, let me say this again. So, time t equal to k is where we are, we assume that the measurement has already come. I am trying to make a control move, for now I am just saying at time t equal to k, and basically I want to make this control move in such a way that all the measurements in the future or predictions that I make in the future, all those values are as close to set point as possible, because I am trying to do this set point tracking here. Now, so this would be y k plus 1 given k. I am showing this as actual measurement, and once we use a model you will see some minor differences there, we will come back to that later. But as of now, whatever measurement I get at k plus 1 given k, k plus 2 given k, k plus 3 given k and so on up to k plus p given k have to be as close to set point as possible. Now, you might be wondering how can you do this, because you are saying whatever measurements I get at k plus 1, k plus 2, k plus 3 all the way up to k plus p are as close to the set point as possible. So, the key idea, this is where the model comes into picture. So, what we are going to do is sitting here we are going to predict what the y's will be. So, this y is actually what is called y hat, which is a prediction for the output. So, sitting at this point what I am going to say is, if I use a model and predict, if I make a change in u, how will the y change over a period of time, and then if I say I am going to see the difference between that prediction and the actual set point, and if up to time k plus p I will make these predictions and see the difference between set point and these predictions, and if somehow I am able to minimize that error, then the actual system in terms of the measurement itself will be close to the set point. For example, if there is absolutely no model planned mismatch, then the predictions will be actually what the measurements will be, and they will be as close to set point as possible. Even if there is some mismatch between the model and predictions, even then there is a good chance that the actual measurements or the actual system output will be as close to the set point as possible when we implement the controller. So, the notion of the model comes here, where I am going to make predictions into the future, okay, and then enforce that the future predictions are as close to the set point as possible. Okay. Now, that part of the picture is done. Now, let us come to this part. So, the key thing to notice is this P, which is called the prediction horizon, which is how many predictions into the future, how many points, right, that you are going to predict into the future to do this comparison between y and y set point. So, that is the prediction horizon. Now, since we are into the business of predicting, so you might ask, why should I make a plan for only time t equal to k. So, I am going to assume that while I am sitting at t equal to k, I am also going to say that I will plan a set of input moves. I will not just say there is this control move that I make only at t equal to k. So, what I am going to say is, okay, if I say this control move is u k, I am also going to plan for u k plus 1, I am also going to plan for u k plus 2, I am going to also plan for u k plus 3, and the last move I am going to plan is u of k plus m minus 1. Okay. So, notice that the control moves that we are planning start from u k plus 1, u k plus 2 all the way up to u k plus m minus 1, whereas the predictions are for k plus 1 all the way up to k plus p. So, this is an important idea to remember. The reason why we start with k for the input, but k plus 1 for the output is because whenever you make a change, I have said there will be some time delay. In fact, if I make a change right now, I will see the effect not right now, because that is a static system. So, if I make a change now and I see a change, that is a static system, but we know that most of these systems are dynamic. So, if I make a change now, it will take some time for the change to be realized. So, if I make a change at u k, y k cannot be changed, right, because it is not instantaneous, but hopefully y k plus 1 can be changed. Okay. So, that is the basic idea here. So, that is the reason why what we will do is once I get a measurement y k, I will use that information also somehow, and then what I will do is I will calculate a u k, because this u k once I implement, that can have an effect on y k plus 1. U k cannot have an effect on y k, because instantaneous effects are usually not possible. Okay. So, what we now say is, okay, I do not want to make one move, but I want to make a move plan. Okay. What is a move plan? I am going to make a plan in up to m values. So, that is this m is called the control horizon. Okay. And how is this m values? u k plus 1, and if you say u k plus m minus 1, u k is 1, u k plus 1 is 2, u k plus 2 is 3, u k plus m minus 1 is k plus m, right. So, there are m values that you have from u k to u k plus m minus 1, and this is k plus m minus 1, because I want to have m values and call that the control horizon. Okay. Now, notice that this m, if it is p, that basically means I make a control move plan till k plus p minus 1, and I know this k plus p minus 1 move that I make will have an impact on k plus p. So, in some sense m, the maximum value it can take is p. Okay. So, then a k plus p minus 1 will still have an impact on k plus p. If you take plan for control moves beyond this, it does not matter, because if I say I am going to plan control moves beyond this, these are not going to have an effect on k plus p, because these are after k plus p. So, when I am trying to only minimize up to here, there is no point in trying to make control moves beyond this point. So, the m is less than equal to p is a general constraint that you can see will happen in MPC. However, in general we keep this m much smaller than p. Okay. So, basically what we are going to do is we are going to make a plan for control moves. So, the idea is, if I make a particular plan like this, how would that change this y if I am able to model this? Then what I am saying is, I can tune this plan in such a way that these predictions are as close to y set point as possible. This is the basic idea of MPC. So, I am going to make a set of future input move plans, and I am going to choose them in such a way the predicted output in a prediction horizon is as close to set point as possible. So, how do we get this mathematically is the question that we have to answer, but conceptually this is what basically happens. And one last thing here, since I am explaining MPC in detail in using this slide, the way actually this will be implemented is, if you are at time t equal to k, you will do this move plan, and then you will get uk plus 1, uk plus 2 all the way up to uk plus m minus 1, and what you will do is you will implement this control move at uk, and then you will wait just like I said here, and you will come back here and you will do the same computation, but now starting at t equal to k plus 1, because k plus 1 becomes the current instant, and then you will compute u k plus 1 again and then implement it and then keep doing this. Okay. So, though you use a move plan at this time and compute all of this, you will not stay with this move plan till you come here. What you will do is, when you go to the next time instant, you will make the next move. The reason why you will do this is the following. So, I gave you this example in the last lecture, where I said why would I even think of a move plan. That is because if I want to get to some place in 5 years, then I have to decide that I will do certain things, not only today, but maybe you might plan for a year and a half into the future, so that in 5 years you will kind of get to where you have to be, right. So, you will continuously plan. So, let us say I plan today saying I will do this for the first 1 month, and I will do this for the next 1 month, and so on, and let us say 1 month later, if I have finished lot more of what I planned, or other things have changed, the environment has changed, so what you planned might not be as relevant anymore. So, what you will do is you will replan again for a 1.5 year period 1 month from now, and then you will do that for a month, and then at the end of the second month you might again look at where you are and replan again, right. So, while you are planning for about 15 18 months, what you do is you implement your first month plan, and then at the end of it you do not stick to the plan that you made 2 months back, because everything changes, right. So, there is environment which is equivalent to disturbances in control and so on. So, what you thought today might not be exactly the same 1 month down the line, not because your thinking has changed, your thinking might still be the same, but the world is moving so fast, things are changing, that you will be forced to re-evaluate everything, right. The same idea is used in control. While you make all of these calculations into the future, while you are at time t equal to k, at k plus 1 you still have to re-evaluate your whole plan and then see what is the best at k plus 1, because you have more information in terms of the surrounding systems and so on at this point. Okay. So, the only question then that begs an answer is, if you are going to redo this at every time k, k plus 1, k plus 2 and so on, why do this move plan at the first instance itself, is a question which is a fair question to ask. And in a more advanced course, I will explain this in lot more theoretical detail. In this class, all I am going to say is this: if you make a plan and if you do not have, let us say, a horizon of planning, then typically what you are going to do is you are going to be very aggressive with your plan, right. So, again going back to the same idea, if you say I want, what do I have to be 5 years down the line, then I am going to plan today what I have to be for what I want to be in 5 years time. Then what I am likely to do is, oh, you will say, okay, there is so much difference between where I am and where I will be, where I want to be 5 years down the line. So, I have to do so many things. So, you might make a very, very aggressive plan for the first month, and then when you get to the second month, it looks as if you have only 1 month to get everything done, though you have a lot of time to get things done, right. So, if you make plans only for the present, then this nuanced thinking in terms of spreading the work out over a period of time does not come in. So, at every move you make, you might be very aggressive. So, you might be all over the place. You might say today, oh, I am very deficient in this, I have to really focus on this and spend a lot of time, and then 1 month down the line you suddenly feel, oh, I am deficient in this. So, you might be all over the place, which is that it might be an aggressive controller from a control viewpoint. So, the idea really is to temper yourself and then say, look, I have bit of time to get to where I want. So, how do I distribute the work that I need to do, or the things that I need to do in a more rational, more stable manner, so that I get to where I want to be 5 years down the line. So, having a horizon like this for the input variable makes the controller more stable, less aggressive, and still at the same time get to where you want to get to 5 years down the line. So, that is the reason why you want to have a move plan every time, and the reason why you want to keep doing the plan again and again, replanning, is because what the situation was here in terms of either your goals or your understanding of your ability, which is the model, or external factors, right. You might think IT is the greatest thing 5 years down the line, a month later maybe IoT is the greatest thing. So things keep changing from an environment viewpoint. So if you are here and you can actually make a move plan again and not stick to the plan you made 1 month back, then it makes really no sense for you to stick to the previous plan. You might always recompute. Now conceptually you can see if this computation takes a long time, then you might say, okay, once I make a plan, let me wait and then make a plan only much later and simply follow through this. But if the computations are handleable or tractable, then you might actually keep making these computations again and again and keep re-evaluating what control moves you have to make. So that is the basic idea in terms of MPC. How do we do all of this mathematically is the question that we need to answer. So now one other thing that I just want to mention here, because we have gone to MPC and kind of talk about MPC as being a panacea for many things, I just do not want to leave the people taking this course with the idea that PID loops are done and dusted with. Absolutely not true, because these PID loops are very critical for maintaining the basic regulatory functions of any plant, and particularly with respect to safety and so on. So typically how MPC is implemented is the following. I just wanted to give you this idea. So if you have a plant, it might have several PID loops already, okay. So these are PID loops, let us say, that are already in the plant. Now when you want to implement an MPC, you are not going to come here and then say, let me remove all the PID loops and implement an MPC. That is not how MPC is implemented. So when you want to implement MPC, what you do is the following. So you say, look, I have some higher level objective, okay, for the plant. I am going to pass that objective on to the MPC, and based on this objective, this MPC is going to manipulate the set points of these PID loops. Okay. So you might think of this as a giant cascade structure that we talked about in terms of the cascade control loop. Here there is one MPC which is going to manipulate the set points of all the lower level PID loops. So the way these set points are figured out is by maximizing some objective, okay, which is a higher level objective. So the outputs are actually related to the higher level objectives, and the model that MPC uses is between the set points of these various PID loops and how the set points of these PID loops affect the output, right. So if I think about this, an MPC controller takes, let us say, some higher level objective and then gives out the set points for this PID loops. So which goes into the process, right, and the process gives me an output, and that is compared with whatever I desire, and the MPC again gives set points to the PID loop. So this is a general structure that is used. So it really does not matter. So what the MPC is manipulating as you are the set points to the PID loops, and the output is are outputs related to some higher level objective, which is what is shown in this picture. There are several advantages to implementing MPC like this. Number one is that all the advantages that you have got out of implementing PID, you do not take it out and then remove it, because the PIDs are still in place. So that is number one advantage. So whatever work you have done till now are all in place, and of course if there are some safety critical loops that require pure safety related attention, it is very difficult to bring that in an MPC framework, because you have to again look at each individual loop and then see whether the objective is to do with safety, the objective is to do with performance and so on. So all of those kind of details can be relegated to a lower level PID control loop or loops, and MPC can really focus on getting something more than what the PID loops are doing in terms of higher level performance objectives. So, that is one reason why the PID loops are there. The other reason, and even more importantly, is that whenever we implement controllers, we worry about the reliability of these controllers, and if you were to remove all of these PID loops and then make them all an MPC loop. So, in other words, there are no set points, there are direct manipulated variables of this PID loops themselves which are being set by the MPC. Then let us say the idea of MPC is to implement this on large number of control loops. Let us say I implement an MPC on, let us say, 40 loops. Then what happens is, if this MPC fails for some reason, right, or decommissioned for some reason for a short period of time, then all of these 40 loops go out of control. Okay. So, that is something that is a very poor design from a reliability viewpoint. You do not want this to happen. However, if you were to implement MPC in this framework where MPC is giving set points to the individual loops, then even if the MPC is decommissioned or taken off for a while, the lower level loops are still going to operate as they have been operating with the set points that they have. Okay. So, in that sense, it is much better to do this structure from a reliability viewpoint. Now, when we actually do this MPC lab part of this course, in all cases we might not look at setting up this problem where there are lower level loops and MPC operates at a higher level. We might show examples of actually MPC directly manipulating the manipulated variables corresponding to kind of seesaw loops, and that type of implementation also does happen if you have very small MPC implementations with 2-3 control variables and 2-3 manipulated variables. It might be better to do an MPC rather than multivariable transfer function based controller design. So, that also happens, but when we really talk about very large scale MPC, then this is the approach that is generally thought of. So, when you see the lab portion where the actual manipulated variables are being changed with an MPC, think of that as actually a larger multivariable control problem than a seesaw 3x3, 4x4, 5x5 and so on. So, do not look for underlying seesaw loops and all that, but what I want to say here is both of these are possible. You can think of MPC for smaller blocks of multivariable control, or you can think of MPC as a large solution which is going to coordinate several underlying PID control loops. So, the advantages which we have already talked about, it can be directly applied to linear and nonlinear systems. This is something that we already talked about. I have not shown how it is going to happen because we have not looked at the mathematical formulation yet, but this is something that we can easily do. It is easy to implement for univariate or single input single output and multivariate or multiple input multiple output systems. It is very simple direct extension, which we will see once we understand how this formulation is done. The ability to include constraints, which is an important aspect. I talked about u, that is the manipulated variable u itself having some bounds within which it has to operate. Not only that, the rate of change of u could also have bounds within which changes have to operate. So, we can include all of those quite easily into the optimization formulation. This is very difficult to do if you are looking at PID, where we talked about just including clipping constraints if you have to include constraints. And the last one is the tuning parameters are intuitive. I have not explained what those are, but in this first level undergrad course, my idea is to get you familiar with this notion of MPC and not think of MPC as something very complicated. I just wanted to explain to you that it is very simple, very easy to move to multivariable control using MPC. So, these tuning parameters and detailed description of tuning parameters I might not be able to do in this course, but once you have this basic understanding, when you look at other material which is little more advanced, then you will be able to easily understand some of these ideas. So, we have already talked about this in detail. detail. At the beginning of this lecture also I started by saying this. The first difference is the MPC uses an explicit model of the process, and the notion of horizon is something that MPC does, which is very different from PID. And the control solution itself is a solution to an optimization problem and not direct analytical expression, though in more advanced analysis of MPC one could see that actually you can come up with some analytical expressions, but you have to figure out in which region you are operating and which analytical expression to use and so on. So, that is for more advanced ideas in MPC. As of now, one can think of this as a solution to an optimization problem, and because it is a solution to an optimization problem, we can include all kinds of constraints that we want and optimally solve for the control move, which would be more difficult to do if you are working with PID control. So, basically the first picture and the whole explanation, if you are able to understand it really well, then the other aspects of MPC formulation become rather simple to explain, which is what I will try to do in the next lectures that I am going to teach in this course. Thank you.